Thank you very much. It's great to have the opportunity to be here and present my work. We are going to talk about analyzing stdf production test data in the silicon manufacturing industry using the construct library. First, let's have a look at the agenda. We will have a look on the background, who we are, what we are doing, also what are stdf files, where are they from what time frame are they, how old are they, and then we will have a look on what we were able to achieve with it, and we will even have the option to look at the performance comparison between the Python solution using construct versus a solution that's using C++ and PyQt and stuff like this. Then we have a second big block where we talk about how we were able to achieve this using construct. So what you need to do, what is construct in the first place, so what is it, what can you do with it, and how can you achieve this. And we will have a look behind the scenes, so we will have a look at how construct works to achieve this, so how does the compiled code look like, but also how does the compiler work that creates the compiled code. And finally we will look into the ecosystem, comparisons, conclusions, stuff like that. So first point, who we are. I'm presenting three groups here. The first group I'm not really part of, but work closely with them, that's test engineering. These guys are building the infrastructure that is used to run the production tests in the silicon environment in my company, in my environment. They make the test programs, they communicate, they build the infrastructure that communicates with the manufacturing execution system that needs to know where is what wafer, in what process step, doing what, with what version, and all this stuff. They write the stuff that creates the stdf files, and they are responsible to keep all this stuff standardized so that our tools work with this stuff very well and make the same stuff for stuff that comes in. So if stuff is from our partners or customers or whoever that sends data to us, they make sure that these files conform to our standards and our internal tools work with it. That's what the test engineering people are doing. Then we have where I'm actually from, that's validation and test development, that's where I'm part of. We do two things. One group of things we do out of necessity. That is, we use the tools that are provided by test engineering to get the data out of production tests. We use other tools to create information out of our lab measurements. And then we combine these sources of information with even more sources of information to get knowledge and make educated decisions. But that's not really the goal we have. The goal we have is that we want to look on when we have a new design that's going to be manufactured, a new chip. We want to look whether the chip design, the masks, the schematics, the production process, if that is good to make a good product. So does our silicon meet the performance criteria we're looking for? Does it do what it's supposed to do? And once that's done, in the production phase, we verify that the production process is still good, so that we don't have a situation where somebody mixed up some fluids or mixed up some masks or something, that is, we are still doing what we're supposed to do. And once that's clear, we want to screen out outliers. We don't look anymore if every chip is good, we only look if all chips are the same. That's what we do in validation and test development. And finally, we have the advanced data engineering folks. And if you look on what they are doing, it's kind of hard to explain what the difference between them is and test engineering. But basically, they focus on catching the data, whereas the test engineering people focus on throwing the data. So when the advanced data engineering people are done, the data has been imported into our databases, and this is the next step before it's acted by the people working in operations. So that's the background of who I am and what we are doing. The next thing is to look at what are stdf files. And stdf files are extremely old technology. It's from 1985. They store the results from the production tests. In the production tests, one or more chips are contacted at once and measured to get some parametric data about them. And inside the stdf file, there is one or more repetitions of this. And it stores the data in kind of a document fashion, but it's from 1985, so the concept of a document database doesn't really make sense in that time frame. But it's a little bit in that direction. The items inside are called records, and these records may or may not reference each other, and they have optional data, and it's an old way of doing things. Just to give you an impression of how long that's ago, that's 1985. The stdf file was invented. Madonna Like a Virgin was a #1 hit. South Africa legalized the concept of having white and black people marry. That wasn't the end of apartheid, that was about 8 years later, I think. The ozone hole was a new discovery, we didn't know that in 1984. The GNU Manifesto was written, and a supercomputer, like the crate on the picture, has something between 2 and 32 gigabytes. And I think there were 25 units built in total, and that was the year it came out, so at that time there were much less. So this is the time frame where this stuff comes from. The next thing is, so what did we achieve with Construct? And what you can see is what I personally think is really impressive. For that particular workload, on the particular machines the stuff is running on, and the system decisions are made by the people building this stuff, to run one on a notebook locally and the other one on a standard workstation remotely. The conversion speed that we achieve is very, very close to each other. The green bar is from the C++ implementation. The red bars are from the Python implementation. They move at about the same speed. It's not a one-to-one comparison because they don't do exactly the same workload, but they start with nothing and they end with the data that they think that the individual developer thought is best to continue to do analysis later with, and it's really in the same ballpark. The only difference is that the Python solution does 8 at a time. So in practice, throughput-wise, the Python solution is actually significantly faster than the C implementation. How was that possible? We allocated our money for hardware differently. We spent a few €100 more and a few years later on a workstation instead on a notebook. That's enough to close the performance gap in this case. The parsing speed differences are all over the place. This is a cherry-picked example. If you take other data, you heat up the notebook a little bit, you cool down the notebook a little bit, you get different results. That was found by accident. I think it's really illustrative that it's just in the same ballpark. You will not get reliable real-world data easily to see what is really better in all cases. That's not how that works. So, next question, how did we achieve that? Well, we did use a really awesome tool, it's called Construct. And they have a really nice introduction on what Construct is. I'm just going to read it to you. Construct is a powerful declarative and symmetrical parser and builder for binary data. So instead of writing imperative code to parse a piece of data, you declaratively define a data structure that describes your data. As this data structure is not code, you can use it in one direction to parse your data into Pythonic objects, in another direction to build objects into binary data. And there's an example of how that can look like in practice. And it is really well approachable in my point of view, and I really like the interface for these old data formats. And the reason why I like this for these old data formats is that at that time, the way people described binary data files was like you see here on the lower corner. You have these columns where you have a name of the field, you have a data type column, you have some description, and then you may have some extra information. And you can literally copy and paste this into your code editor, and then you make these large cursors, and you go through to replace whatever symbol the origin author used to separate columns to whatever is the proper symbol in Construct in that case, and you're done. This is, in an absurd large amount of cases, already good enough to work. You may still need to do stuff to make it fast and to make it react to certain situations, but this is surprisingly often good enough. So, next question is, what did Construct do for us? And once we have done this, which was really easy, we were able to use it to solve problems we have very efficiently. What you see here is real-world code. We really use this in some situations to rename stdf files so that the file name matches the metadata inside the file. That is very helpful for people who want to use file operations to move data around. It's really helpful and makes it really approachable. It's really easy to implement that, to change that, to add new features if it's needed, because it's really so little code that it's easy to handle. We will go and look at a comparison to an alternative implementation in Perl later in this talk. The next thing we're able to achieve is to write a simulator. One of the problems you have when you run test programs is that they run on machines that are really old sometimes, but always very expensive. You have to book them in advance. You need an operator that is trained to use them at the place. You need to put the stuff in. You can, if you have a wafer, you can only contact it a couple of times until the needles have poked through the metal and they're broken. So you want to avoid that for many reasons. And what the simulator allows us to do is it's the same code that generates the stdf file, reads the stdf file. When it comes to a point where a change in the limits, we cannot change the execution of the test program runner. They can change the interpretation of the result. So when it comes to the limits where it interprets the measurement data from the automated test machine, it stops, uses the new limits and writes a new stdf file, so we are able to rerun the measurement simulated way without using hardware in an extremely fast way compared to the real world, very cheaply, very efficiently, very little code. That's 19 lines. That's virtually nothing. So what is here behind the scenes? How does it work behind the scenes? So let's go back to such an example where we see these tables and have a look on what comes out when you run the compiler. And what you see when you run the compiler, the functions that come out of, they are ugly to a large extent. The file names are ugly. There are names all with numbers in them. That's not nice. But it does a lot of the optimization stuff already for you. So the struct.unpack, that is compressed. It doesn't do it for every element. It does it for all the elements in a row. So that's already close to the optimum. The dictionary is created at the end, so you don't have a lot of dictionary lookups and modifications. It's just on one step that is already close to the optimum. And if your file runs out to the end, it will early out. It will say, okay, the file is over. There's nothing coming anymore. I abort. So yeah, this is my point of view. Good. This is amazing. That's great. I promised that we can have a look at an alternative solution for the renamer in Perl. And there's one thing that I really like about this. The first thing is that my colleague who is in charge of the Perl script was willing to provide the script as a comparison. I think that's awesome. But also the fact that the compiled result and the Perl result have so many things in common. When you look at this long string on the Perl up there, and then the quite shorter string on the Python on that side, they're the same. You make a lookup table that replaces, I think it's the capital L's with the capital N, and you come to the same solution. It's conversion design. So two approaches lead to the same result, which is a really good sign. The big advantage of the construct solution is that the engineers who work with that don't need to deal with this. They need to deal with that, which is way more convenient, way more efficient, and also way closer to the way you want to communicate with your colleagues. You don't want to tell them what it's line 150 is happening something. You want to say, well, I'm in the MIR workup on the port code, one character thing, and I expect something else than I see there. What's wrong, or what's going on? So this is really, for me, the big winner of the construct solution. Now, finally, we'll have a look at how the compiler works. It's not complicated, it's not rocket science. It is a big speed improvement. If you don't have this compiler stuff on one of the structures you use in construct, it's much slower. It goes back into an interpreted or non-compiled version of the same feature, so it's just much slower. And it's really easy to do. In that case, it's the example for a C string. A C string is a bunch of bytes that are non-zero, ending with a 0, unless it's a V2DF encoding, then it may need 2 zeros or 4 zeros or whatever. And it's just a loop that reads one group that's large enough to be interpreted as a character, compares it with a terminating symbol, and continues reading until it finds the terminating symbol. That's the function. And then there's a line that is emitted whenever the construct library thinks it needs a C string parser that just calls that function. It's not complicated. And if you have a better way to implement reading a C string, that's awesome. You just need to replace it here, and it spreads all over the place. So that is, don't be afraid of that. If you think something is too slow, just go there and look at that. And if you have already your idea in mind how to improve the speed, it's normally not too hard to do it. And you can also look at the compiled result. So if you disagree with something, you can look at the result and think, oh, that would be better, I can go there. It's not hard, it's actually fun to do that. So we now come to the reasons why we chose construct. And the reason we chose construct are the advantages in our view. So that copying the specification into our code is a huge advantage for us. You don't even need to deal with the compiler, you can just start immediately. If you do compile it, it's just about, I don't know, 10 letters more to type. It's really, really great. The documentation travels with the implementation. It doesn't go with the data that is parsed, but it goes with the implementation. So when you're looking with, you have something that's a construct parsing or building object, you don't know what that thing means, you have the document string available under the name .docs, which is really helpful. It's not something you wrote for your manager and never use it. The parser and the generator share the same bugs. So when I made a mistake, the mistake is the same when I read it and when I write it, and that makes it much easier to deal with the problem and recover from it. In most other situations, the parser and generator bugs are unrelated, and that makes it much harder to fix the situation. Maybe not to fix the situation, but especially to understand the situation. It's two problems instead of one. And one of the two problems may not even be a problem. It's even more frustrating. Compared with the alternatives, it has a really active community and it has a reasonably large user base. There are millions of downloads on PyCon. We also looked on other solutions. There's KaiTai. They have a symbiotic relationship with construct, so you can take a construct and ask it to create a KaiTai script, and then you, I don't know, definition, and use that with the KaiTai tooling if you want to. There's Mr. Crowbar. KaiTai doesn't have a generator, it's only a parser. Mr. Crowbar has a generator and a parser, and the other Hakwa has no generator, and Caterpillar hasn't made a public release yet. So the fact that we have such an active community there and linked community so that the KaiTai stuff is available via construct triggered us to go the direction of construct. Also, construct is a very, very established technology. The oldest download you still get on PyPy is from 2013, and the oldest commit in the code base goes back to 2007. That is really well hung software that is still maintained by some of the original authors. I reached out to them. I got answers of 2 of the original authors, and one of them is also pretty active on GitHub still on the project. I really like that. Then let's come to the conclusion. Construct-powered parsers can achieve competitive speeds. To do that, I used PyPy to read the binary data, and then I passed it on to CPython to write the Parquet files. So it's a little bit of effort you have to put in, but it can achieve competitive speed to C implementations in the real world. That is, I was surprised by that. I actually didn't expect that in the beginning. If the people working with other languages would make different design choices, it probably would become impossible. But in this particular case, with this particular feature set, it was possible to achieve that. And the speed we were able to react to unexpected problems and fix them using this construct library is impressive from my point of view. This here is the smallest example that I actually used in the real world. It's, I didn't count it, but it's, I don't know, 10 lines of code, maybe 15 or something. And it's already solving a real world problem. That is just amazing in my point of view. The stdf parser stuff is open source. It's available on the company GitLab page. And yeah, we achieved a lot of successes with that. Finally, thanks for your attention. Special thanks to my colleagues. Ahmad Abdelmajid was even willing to provide me the source code of the Perl script to compare to, which I think is absolutely awesome. Roman Steiner reviewed a lot, and he used the fact that stdf Thema is open source to build on top of it. So because it's open source, it's easier to move not only outside of our company, but also inside the company, and he was able to use it to make a tool that shows him the data that he's interested in without negotiating with somebody why he's interested in that data. Stefan Krasser for providing review and slides, as well did Ahmad. And to the contributors of the Construct project, so Arkadiusz Polski, Corbin Simpson, Thomas Philipp are the original authors that are also noted in the license file, but there are also other contributors, and it's a really awesome tool that I really recommend to look at. Thanks a lot for your, thanks a lot for your attention, and I'm looking forward to questions.
So the parsing of these files, that was the performance of that was a constraint in the wider business, just how long it took to parse them?
No, it's not. All the parsers I worked with are faster than the network.
Mm-hmm.
So if you make your parser even faster than that, it just waits faster.
Right. Okay.
And you save some power and stuff, but it's not really solving any problems. The only thing that's interesting speed-wise is that if something goes wrong and the maintenance guy is right at the machine and he double-clicks the file, he wants to have some information immediately.
Yeah.
But the people who wrote the files wrote it for very weak machines, so this information is on the first few hundred bytes, and it's
right.
Not a problem.
So you mentioned some comparison in the speed a few times. So how much time does it take to parse one file, for example, before you use the construct, and how much time is now?
The same. So the C parser takes roughly the same time as the construct parser for this particular temperature of the notebook and this particular file and all this stuff. But this, under some circumstances, it takes the same time. But the construct-based solution is capable of using the multiple cores in your machine better. The C++ implementation uses a GUI framework that ties it to doing stuff in a certain way if you want to have the fancy GUI features. So you have to copy the file first and then you start. And at that point you actually already have lost.
But are we talking about seconds, minutes? What is the scale for the
The scale is really depending on the product we're working on, and it is for the files I'm most of the time working something in the 20-second range or shorter.
Have you tried using construct for other data formats?
Yes, a lot. We use that a lot to describe the registers in the products we're working with. So our chips have typically 8 bytes, sometimes 16, no, not 8 byte, 8-bit, sometimes 16-bit registers. And in these registers, there are bits that have a different meaning than others, and sometimes 4 bits make an integer or whatever. And that's basically where we started using it. At that time, we really didn't care about speed because we have, I don't know, 10 bytes to work with, 20 bytes to work with, so nobody cares. But that's how we introduced it into our workflow, and we looked at the stdf file basically as just a very big register map, and that works, and it's awesome in that use case. Yes, thanks. That's a good point.
Is this construct actively maintained?
Yes, it is. Yes, it is. So the Arek Pulski is still reacting to GitHub issues. It has. It's not a fancy project. It's from 2007, so they have the hype cycle long behind them, and they are slow in change compared to Polars, for example. That Polars probably releases 10 things before Construct releases 1, but they are still there. Still people answering stuff. There's still a use base. It's just a good thing that does what needs to be done well.
And what version of Python are you using?
The best speed I achieved with Python 3.10. No, 3.11, sorry, 3.11 was the best one. 3.12 is slightly slower. And for PyPy, I have to admit I would need to look it up, whatever was recent 2 weeks ago.
So I think you showed this, but I'll ask the question anyway. So in terms of explaining to construct new data types, so I maintain a binary parser which has to deal with some custom floating point types.
Yes.
So I could write Python functions which explain to construct how those types are laid out.
Yes. Okay. There's a data type. There are actually 2 ways to do it, but there's a data type that you would inherit from and then explain that. There's a different approach whether you have stuff that's working with bytes boundaries, or with
Bits.
just bits.
Yeah. Okay.
And the C-string stuff, for example, the compiler for that is written by me, which I just showed. It's not hard. I like it. It's fun.
Okay.
Okay. Well, thank you to Franz. And,